So we're going to learn a shorter, sometimes shorter, method for computing determinants, as well as several computational properties of determinants. All right, so I've got a 4x4 matrix here. I want to find its determinant. A cofactor expansion would be really tedious in this case because I don't have a lot of zeros. There isn't a column or row that makes that nice and easy. So instead, I'm going to use this theorem that relates a matrix and its row-reduced equivalent matrix and their determinants. So here's the theorem. It's written here in bold from your text. If you do a multiple of one row of A added to another row to produce a row equivalent matrix, the determinants of those two matrices are the same. So that's the most common row operation we do when you're row reducing. But then there are two others. If you interchange two rows, just swap their places, then the determinants of those two matrices are opposites of each other. The sign just changes. And if you multiply one row of a matrix by a constant, then we already learned this one in the last lesson, right? That if you multiply one row by a constant, then the determinant also changes by that same factor. So I've got this 4x4. I'm going to row reduce, and the reason that this theorem and these three rules are helpful is because if I have a triangular matrix, if I can get this thing into echelon form, its determinant is just the product of the diagonal entries. So I'm going to do some row operations till I hit echelon form, noting how the determinant changes, and then I'm just going to multiply the diagonal entries. So I start with this, and first thing I want to do is work down the first column. I want to knock out everything underneath the 1, right? So my first step here is going to be, actually I'm going to use an equal sign because I'm talking about the determinant of these things, right? So if I want to create a matrix with the same determinant, I can do a row operation where I replace a row with a multiple of another row, and the determinant doesn't change. So I'm going to replace row 2 becomes row 2 minus 2 row 1. And when you do a row replacement like that, the determinant doesn't change. So I can use an equal sign. So 1, -3, 1, -2. And my row 2 is going to become 0, 1, -3, 2. And then I also want to knock out this -3. And in the past, I would have you write it out in a separate step, but I'm just going to do it in the same step. So I'm going to have row 4 is also going to get replaced here. Row 4 becomes row 4 plus what? 3 row 1. So row 3 is not going to change. It's already got a 0 where I want it. And then row 4 is going to change according to this rule, and it becomes 0, 1, -3, 2. And because all I've done here is row replacement, replacing a row with itself plus a multiple of another row, determinant doesn't change. If I swap two rows, the determinant changes sign. If I multiply a whole row by a constant, the determinant changes by that same constant. All right, now what I got to work on? Now I got to work on the second column. I need everything under the 1 to be a 0. So I'm going to do, again, just row replacements. So let's see, row 3 is going to become row 3 plus 4 row 2. And row 4 is going to become row 4 minus 1 row 2. All right, so this is 1, -3, 1, -2, 0, 1, -3, 2, and then row 3 changes to 0, 0, -7, 9, and row 4 becomes 0, 0, 0, 0. What 0? The determinant, yeah, because I now have this in echelon form. I have a triangular matrix with zeros underneath the main diagonal. So my determinant is the product of the diagonal entries. So the fact that the determinant is 0 here tells me that the inverse of this matrix does not exist. And then the whole list of the invertible matrix theorem now applies, right? So if I know that the inverse doesn't exist, I know that the columns of this matrix are linearly dependent, right? So that's what finding determinants is useful for, right? You can use it to answer any kind of question about the invertible matrix theorem, right? If it's easy to find the determinant, that's one way to quickly answer all those questions. And if you wanted to find the inverse, whether by hand or on a computer, if the matrix was large, it's helpful to know whether the inverse exists before you start trying to find it, right? Because row reducing takes a lot of work. So if you have to row reduce to find it anyway, you might as well pause at echelon form and see if the determinant exists. Okay, so here's a corollary to something that you already worked on in the previous lesson. But in the previous lesson, we were talking about a 2 by 2, right? And now we're talking about an n by n. So when it was 2 by 2, what we learned was that the determinant of Ka equals k squared times the determinant of A. So that was, I think, number 5 in your activities. Okay, so what do you think the rule is when you, instead of a 2 by 2, you're now working with an n by n? K to the n, yeah. Because now instead of multiplying 2 rows by k, so according to our rule about determinants, that when you multiply a row by k, the determinant increases by that same factor, changes by that same factor. So now I'm going to multiply n different rows by that factor k, so you're going to increase the, or change the determinant by that factor n times. So for an n by n, the determinant of Ka is k to the n times the determinant of A. All right, so that's it for the demo portion. You can either go back and pick up where you left off or start these activities, work on them. As much as we can get through today, it will be good to have a little extra time for the first part of chapter 4 on Thursday.